All right, class. Yeah. All right. Good morning, class. Took a little time to get in. All right. Okay, before we get started, any questions? Update my other computer. Cut my phone off. Questions? Okay. All right. Let me go here. So no questions. All right. Everybody took the test? Oh,
Yeah.
Yeah. I got your email. I not yeah, but you having issues and whatever. Yeah. But what happened though? I don't understand.
I just had to keep downloading it. I don't know what was going on. And I even took it to our IT department. I don't know if it was my laptop or what. I don't know. But I had to do it like several times in order for it to accept.
Yeah, it's something like I said, you're adding that extension into the browser. You may need it to have closed the browser out and then come back in so it
Well, that's what I did, but it was like the only part was I couldn't share it. That was the problem I was having.
Oh, with the monitor, okay, with the people monitoring it, okay. And it could have been something that you had restricting it in your software. I mean, on your system.
No.
It wasn't?
I don't know. IT did it for me, and I thank God I finally got it.
Okay. All right. So.
Mr. Sylvester?
Yes, who is this?
Mr. Gyro.
All right, what's up, Mr. Gyro? What you got?
Is the roll working now?
Nah, not yet. I keep forgetting to go into that. Go ahead on and put your names in.
That's an extra 20 points for us.
No, that's minus 20 because I got to do more work.
Yes,
So just put your names in the chat. Now, the next chapter, like I said, we dealt with arrays, and we said that arrays were pointers or addresses, memory addresses that you actually was referencing to get the values from those positions. So this chapter deals with pointers, okay? Pretty much the same, but it's gonna be a little different, okay? And programming, when you're programming with pointers, you know, like I said, you really gotta know what you're doing, remember what you did and where, because you could be thinking that you're pointing to a particular value or address where you're pointing to a different one. So it can get confusing. So it says getting the address of a value. So it says the address operator, which is your ampersand, all right, returns the address of a value. Okay, so what you do is you can use that ampersand to tell, okay, what address is, like if I say int x, and then I can create a pointer variable to store the X address. Now the address is what? The memory location of where that data is stored. Okay, so you gotta understand sometimes you can pull the data from that address, but pointers deal with actually referencing that memory address where that data is being located. All right. So it's kind of like dealing with the post office. The post office deal with addresses, right? Not necessarily the people who live at that home. It's the address, all right? So every variable is, well, do I have my screen shared? No, I don't. I don't think so. Okay, let me share my screen. All right, so is my screen shared?
Yes, sir.
Yeah.
Okay, so it tells us that every variable is allocated a section of memory. And all that's saying, just like when you build a house, you cannot just build a house and there's no address. It's some type of physical address, whether or not it's a PO box or an like say that with a 911 a physical address. And the same with variables. You cannot have a variable that's declared in your program and it doesn't have a memory location allocated for it. Because when you do, that's why it's important, or that's why you do the int x or char letter or whatever. When you do that, you actually allocating a memory location for that variable. Okay? So every variable is allocated a section of memory large enough to hold the variable of a value of the variable data type. Because remember what we said before. Remember char data. How much space is allocated for a char variable? 1 byte. You see here? So that's how the system goes in and grab that data. Shorts. Short data is 2 bytes. Int, long, and float, all right, and this is long int, is all 4 bytes. And then you have double, which is 8 bytes. So see how what happens is if I declare a variable that's double, the system says, okay, I need to allocate using 8 bytes a variable, and it could be amount, okay? So you have that starting address. Now the system, it knows the starting address, but with the data type, it knows what? How many byte long that variable is allocated for. And it can read that information in those, 8 bytes. So that's how the system goes in and recall data. Each byte of memory has a memory address, okay? A variable's address is the address of the first byte allocated to the variable. So remember when I said that double, it has a memory address, that beginning point, but it knows that it stops at the 8th byte, all right? So it knows to take all that and read the value from those 8 bytes, all right? You have char, okay? Char letter, and this is just somewhat of a representation. Say that this line says each square is a byte. So what happens? Char letter will take on 1 byte, okay? It'll take up 1 byte of memory. Then short number would take up 2 bytes. Then we have float amount will take up 4 bytes. Now, we know that with the computer, a lot of things is done randomly. So the memory might not be in consecutive order. You might have something stored somewhere at one particular address, and then the short is stored at another address, but it's not in sequence. You understand? But the system knows where to go and retrieve that data based upon the bytes, the starting address, and the byte size or the data type. Okay? So the addresses of the variables above are used just as an example, just so you can understand how data is stored in. Because this is 1 byte. So from this here to here is just that 1 byte. But notice here, short has 2 bytes. It started at this, so say address 1201, but then 1202 is here, but it ends at here at 1203. So you got 1, 2. You got to take this address and this address, or really this address, and do 2 bytes. This is the float, 4 bytes. So you start at 1203, and then it takes up the next 4 bytes to grab the data that's stored at that memory location. All right. So the address of the variables above are used as an example. Getting the address of the variable, all right, is accomplished by using the ampersand, all right, the operator in front of the variable name, all right? So it allows the system to return the address of the variable in hexadecimal. Now, class, what hexadecimal is? Hello?
The 6 decimal.
How many?
6 decimals.
Is what?
Wait, it's not 6 decimals?
No, it's not 6, hexadecimal.
Dang.
What base that is?
Dang.
Remember from 192, we dealt with base 2, well, base 10, which is was number or decimal. We did with base 2, which was binary, base 8, which was octal, and base
6.
6, not 6.
16.
16, which was
There we go.
hex. Right, remember? So that's what that is, okay? A hexadecimal address. All right. Now, so if I think I got visual. Visual. So if I go to Visual Studio, I should open up a project. All right. Well, I should have just opened up a project. All right, just so open up this project, and hopefully it's a program that was written, simple program. All right. Just dealing with, okay, let's just take this out and we'll do something like int x. Let me make this a little bigger so you can see. Okay. Too bad. Okay. All right, int x, y, let's see. All right, so if I say x, let's say x, and I don't have to do it that way, but I'll just say x equals 5, y equals 3, 2. But if I do a cout, just double space and then move it over. And I'll do the X address, all right? Me and this keyboard here. All right, I'll do the address of X. Now, to do the address of X, I'll just do this, all right? But if I output X, I didn't need this up here. I'm gonna do all that. And if I go down here and do, I'm gonna just do Y. Okay. All right, and do the address of what, well, not say X, value of X. Okay, I'll just wait on Y. All right, and so for me to get the value of X, I'm gonna just output what? Output X, right. So X. So watch what happens. Okay, let's bug it because they're already existing. So, all right. So notice what happened here. The address is what? This information here, right? But the actual value is what? 5. All right, that's stored at that memory location. How did we get the address? We got the address by what? Using the what? Ampersand. All right, we got the actual value by just using X. All right, so that's what's happening. So what? 5 is actually stored at what? This address. Everybody understand that? It's stored at this address, but the value is this. Okay, so just trying to get your heads up. You can kind of understand once we get started. Now I said don't get confused. Don't confuse the address operator with the ampersand symbol used for what? Referencing for defining a reference variable. Because you know what? When you're dealing with your function headers, what? You're dealing with your reference variable that you passing, you know, that value by reference, which is you're still passing it by the what? The address, correct?
Yes, sir.
All right, so remember that. All right, so remember that. So now, so look at this small program, which is somewhat of what we wrote a little while ago. It got int main, all right? It got x is equal to 25. If I want to output the address of x, what? Ampersand x. And look what it printed out, the memory address. I printed out the size of, because size of is a function, all right? You can call that function kind of like the power function, what else? All these other functions that are used within C++. So size of, and then you put the actual variable, and it'll give you the byte size that's allocated for that memory location. But then, just to print out the actual value of x, we'll just print out what? X, which is the variable name we declare and then assign that value to it. So see, same variable used in all three outputs, but this was the what? The address, this was the size of, and this was the actual content, what's stored at that location. Okay? Questions? Okay? Now, it says pointer of variables or pointers are special variables that hold memory addresses, a memory address. Just as int variables are designed to hold integers, pointer variables are designed to hold memory addresses. So you got to understand, a variable, or just the normal variable can hold, like say an int variable can hold int data. A pointer variable only holds the what?
Integer.
The address. A pointer can only hold an address. Now, there is a key though with pointers. If I declare a pointer to be of integer, we said it only can hold an address of what? An integer, a variable, right? Well, how to say that? Well, it only holds an address. But if I declare a pointer to be int, it can only hold an address of an int variable. If I declare a pointer to be of a char, it can only hold the address of a char variable, all right? If I declare a pointer to be of double, it can only hold the address of a double variable. Everybody got that? So I can't declare a pointer to be of int and then store a double a pointer address into it. Can't do that, all right? So it says, I think we read through this. Just as a int variable is designed to hold integers, pointer variables are designed to hold memory addresses. Pointer variables allow you to indirectly manipulate data stored in other variables. So that's what makes it kind of confusing and tough to deal with. Memory addresses identify specific locations in the computer's memory. Because what? I could write this program that I have where I declare X, Y, and Z, and then I gave X a value. Then I printed out the memory address, the size, and then the value. I could run it on another computer. I'll get the 5. I possibly would get the size of, the right size, but I would probably also get a different what? Memory address, correct? Because when I run it on my computer, the memory address allocated has to be some free memory, something that's free, so I could put it there, allocate it. So when I run it on another computer, if that memory address is taken, or if the system is configured different, the address for that memory, that variable, will be totally different, all right? Because the systems are set up different, all right? So when you run, but it doesn't make a difference where you're pointing, long as you pointing to that reference for that variable. So that's the difference in it. You might have a different address, but long as you point to it, you know you're grabbing the data that's at that memory location, all right? So because pointer variables hold a memory address, it can be used to hold the location of some other piece of data, all right? i.e. points to some piece of data that is stored in the computer's memory. Pointer variables allow you to work with data that they point to, just repeating. And like I say, when you deal with pointers, when you program with pointers, your program tend to run faster because you're programming at a low level, in a low level language, all right? Not language, but in a low level, which the system don't have to try to, what's the memory location? What's the data type? What's the byte? No, this is the address, boom, I know where to get it, do whatever. So it's working a whole lot, would be working a whole lot faster, right? So it says here is where we're passing the name of an array on numbers, all right? And its size as an argument to show val function. So here you have int numbers and then size, all right? And it initializes it to 1, 2, 3, 4, 5. But then here is why we actually calling this function. We passing numbers into what? Values. And really what we're doing, we said an array, this is an array, right? An array is a what? A pointer. Everybody got that? An array is a pointer, right? The name of the array is the starting address of that array. So when I pass numbers into this particular array, I'm actually passing the what? Anybody? What am I passing when I pass numbers into value?
Passing a data point into into the memory location.
Right. Well, what am I? I'm actually passing the address. If you understand what I'm saying, I'm not actually passing all these numbers or whatnot. I'm passing the what? The address. Right. Because remember we said arrays are pointers, correct? So once we pass numbers into values, it's passing that memory location to this, and that's the starting point. Now, how does it know how to pick up those numbers? Okay, if value, which is the name, it was numbers, but we passing it the starting address into values. So values have a starting point. Okay, now how does it know how to pick up each number? What's the data type?
Int.
What's the byte size?
4.
So every 4 bytes will be the next what? Value that it needs to pick up. So you see what's happening? That's how pointers work. So what happens is the name of the name of the array, that's the starting point. So sub-0, that's the starting point. So when you bump it up to 1, it moves to the next 4, 2 to the next 4, and on and on and on. So that's how it works. All right. So you can use values in here and manipulate it by what? This subscript, and it moves what? Every 4 bytes till you get to the end of the this till you up until size till you get to the end of the array. All right. So it says the values parameter, all right, receives the address of the numbers array. It works like a pointer because it points to the numbers array. So you're working with values, but you're really manipulating the data in what? In the numbers array. All right.
I mean, an array is just a pointer.
Correct, and that's what I keep trying to stress. That it's a pointer. It's a pointer. Right. And that's why you didn't have to pass it by reference. Remember when we was doing vectors and whatever and other numbers? And in order for that number not to have changed when we go back to the main function, we had to pass it by reference. So that what? When we pass by reference, we pass in the memory address so that whatever we do to that variable is automatically done, right? But if we just pass, like here, it's constant. But if we pass, say size was not constant, and we pass size into this size here, what would happen is if we incremented size or divided it or did whatever, like say size plus plus, when we return back to here, size would still be the value when it left this function here, the main function. But if we would pass it by reference with the pass size and then put ampersand size here, whatever we did to this size, what? We moved the address into this, and therefore it would what? If I add 1 to this, when I return here, size would increase, okay? Now that's disregarding this because we know this is constant, but I was trying to give an example, right? But everybody understand that. So this kind of talking about the same thing we've talked about already. This is our numbers array, all right? It's initialized to 1, 2, 3, 4, 5. So when we actually call that array from the main or from whatever function, from the main function, show value, we're passing numbers and we passing size. It's actually passing what? The address of numbers into values, which is an array, which is a pointer, which would be the address. All right. So you're passing that starting address so that when you start your loop here, then that's when it will increment on and on and on to move 4 bytes at a time. All right. And this should be equal. I don't know why I got this. This say count -0. This should be equal, class. I need to fix that. All right. Everybody see that? I need to fix this. This should be int count equals 0. All right. So it says inside the show val function, anything that is done to the values parameter, right? So that values array, whatever is done to values is automatically done what? To the numbers array because we passed the what? Address, right? Just like I was telling you about size. If we had an ampersand here, passing it by referencing the address, whatever we do to size here, it would change this. But if we have this constant and we pass it by reference and we try to increment count, we're gonna get an error because it's knowing that we trying to change this. Okay. All right. So it says value of parameter reference in the numbers array. Okay. So now let's look again at passing by reference. So we have a variable called jelly donut, okay, of integer. It's not a constant, so what? That value can be changed. So, and I'll write a little program to show you. I think we've done it already, but I'll just show you. This says, this is calling a function called get order, okay? And then what? We pass in the what? The value of jelly donut to scratch that. We're passing the address, but I have to look at this. If the prototype was there, we'd know that we're passing the reference. So we're passing the actual address. We're pointing to that address. So donuts here is the address, is gonna have the address stored here. So anything we do to donut, all right, donut will affect jelly donut, all right? So what that means, if we return back to this function here and we inputted donuts here, when we get to this, when we get back to the main function, it will have the value that was inputted in this function. But if we'd have just passed jelly donuts in the donuts without this, we could input donuts, but when we return, jelly donuts would still be nothing. You got what I'm saying? Because it would not be changed, right? So it says in this function, the donut parameter is a reference variable and receives the address of jelly donuts, or the jelly donuts variable. Anything that is done to donuts, all right, in here, is actually done to jelly donut variable. All right, so let's look at a small program. So let's say I could take this out. Let me say something like say int age, all right, int age, and then I'll do something like and I'll multiply times 2, get age, and then I'll pass age. Okay, I'll pass age. So I don't want this. All right. So what I'll do, I'll go up here and I'll declare my my prototype. Void get age. All right, and it'll be int. All right. All right. So all it's saying is I have a function called get age. Nothing is being returned, but I'm passing an int, all right? So here, an int, all right? So now, I'll go down, and then what I'll do this. Well, I'll just give it a value here. I'll say age equals 0, just to show you. And what I'll do C out age, C out. Boom. All right. So now, what I'll write the function void get age, and then I'm passing an int, and I could say a, but we know it's age. I could have used age because it's a different scope. All right. Now I could say see out input your age. I forgot my semicolon. And then what? CN a, not age, A, right? And then it'll return. It's gonna return, then I'm gonna print out age, all right? But looking at this, let's look at it, okay? Age is 0. So what we're doing, we calling the function get age. Okay, this will pass the value 0 into A, right? Everybody with me? Now it says input your age, all right? CN the value for A, all right? We have 0 here. So now if we put in 25. So now A becomes what? 25. But when we return back to the main function, what happens? What's the value for age? Huh? What's the value for age?
Wouldn't it be 25?
Nope, it's 0, because remember the scope of age is what? The main function, correct?
Right.
So when we pass age, we only pass in the what? The integer value. You understand? So we pass 25 here. It does not reference age in no kind of way. All we passing is the what? The value. So we pass 0 here. CNA, A is, we put in 25, but A has a what? A scope of what? Just get age, right? So when we return back, now we dealing with the age that's in here. So you say, well, Mr. Vester, I can't understand why. Let's look at it. Let's run it. All right, let's run it. Okay. Hopefully I got all the errors up. Whatever. Oh, it's down here. All right. So look, enter your age. So I put 25. When I hit enter, it's going to return back to the main function, and now it's going to execute the next statement after the call, and it's going to output age, but it should output what? 0. Everybody understand that? Because I just passed the value. But check this out. When I do this, okay, now I'm telling it, when I pass age, I'm going to pass what?
Pass it by reference.
Which going to be the what?
The address.
That address. So now I got to go over here and put the ampersand here. So now what it's saying, go to that address, pass that address. And so whatever I do it at that address. So when I put in the value for A, I'm actually doing it where? At that address. Everybody understand that? So that it automatically will, whatever I do here for this variable, this reference variable, would automatically be done to age when it happens. So let's debug it. Let's run it again. Let me close this one up. All right, let's debug it again. So let's run it. Okay, enter your age. I put 25. You see what happened? Same program. All I had to do was what? Reference, pass by reference. Everybody see that? Confusion? Anybody? Questions? Questions? Anybody? Everybody see how the first time through, I didn't pass by reference. I just passed that value of age. But the next time, I said, well, I'm gonna pass by reference, meaning anything I do to this variable here will automatically change the way I passed the address. What happened? I touched the screen. The address where I passed it, with that I was passing. All right? Questions? Questions? All right. So let's go back to our program. So that's what this is actually saying. So here again, it's telling us jelly donut variable, okay, has an address. When we do the ampersand, what happens is it does not pass the value, but rather it passes the address. All right. So it's going to take that address because we have ampersand here, and it's going to take that address and pass it into donuts. And anything we do to donuts is automatically done to jelly donuts because we're working at the address level. All right, everybody understand? So when the user enter a value, the CN statement uses the donut reference variable to indirectly store a value in the jelly donut variable. The connection between the two variables are automatically established because of what? The address, all right? It being the reference, all right? So that there's no need to worry about finding the memory address of jelly donuts. Now, that's good because what? Like I told you, I could take this particular code and run it on another computer. It don't matter where it put jelly donut, what address. It's just gonna say, well, when the variable declared on this computer for jelly donut, it's here. So when I pass it, I know where it is, and I'm gonna pass that address. I'll use that address. It's done. When I use that code on another computer, same difference. I might get a different address for jelly donut, but whatever address it allocates, that's the address that's going to be used to run the program. All right. So that's how it works. All right. Now, it tells us, and this is some instructions, in C++, pointer variables are yet another mechanism for using memory addresses to work with pieces of data. Pointer variables are similar to reference variables, but pointer variables operate at a what? Lower level, which means your program runs faster. This means that C++ does not automatically do as much work for you with pointer variables as it does with reference variables. In order to make a pointer variable reference another item in memory, you have to write code to fetch the memory address of that item. So rather than doing it like, you don't have to just use reference variables in function calls. You can have pointers created and have those memory locations allocated to those pointer variables. All right. So it's so it can fetch those memory addresses of that item and assign the address to a pointer variable. Also, when you use pointer variables to store a value in a memory location that the pointer references, your code has to specify that the value should be stored in the location referenced by the pointer variable, okay, and not the pointer variable itself, because the pointer variable only can hold addresses, okay? The pointer variable cannot hold the data that's stored at a memory location. It only stores addresses, okay? So as you can see, reference variables are easier to work with, but pointers are useful and even necessary for operations such as dynamic memory allocation. All right, because like I say, and allocating it, whatever computer you're on is allocated so that you don't have to worry about that. Okay. Algorithms that manipulate, and then also algorithms that manipulate arrays and C strings. All right. So it makes it better for you to use. Now, creating a pointer variable. It's not hard, class, but like I said, you got to remember when you create a pointer variable, that pointer variable can only hold memory addresses, all right? And if I have an int pointer, that int pointer can only hold memory addresses for int data, the int variables. So this is an example. If I wanted to create a pointer variable, I could do this, int with the asterisk and then the name of the pointer. Long as the naming scheme is what? The same as when you create a variable. One word, which means no spaces, doesn't begin with a number, and no special characters. All right. So, like I say, you can create a pointer variable. So this would allow you as a programmer, when you do this, that will allow you as a programmer to store any int variables memory address into this PTR, which is a pointer. All right. So the asterisk in front of the variable indicates that PTR is a pointer variable. Okay. Int data type indicates that PTR can hold the addresses of, and I should say only, integer values. Okay. The pointer address or the address of integer values. Okay. Note, int does not mean that PTR is an integer variable. No, it doesn't. But rather, PTR can hold the address of an integer variable. Okay. Pointers can only hold addresses. Got to remember that. Only addresses. So now, looking at this, this is just what? Programming style. You can do it this way, int space, asterisk PTR, semicolon, or you can do int asterisk space PTR, semicolon. Both of them will work. It's all in what? The preference of the what? The programmer. So that's just programmer style. All right. So let's look at this small program here. And we somewhat done this already. No, we didn't. We just actually printed out the address. But look at this program. This program says what? Int x equal 25. So we just declared a variable of integer data type to be called x and is equal to the value 25. So what happens in that one statement? When the compiler sees this, it says, okay, I see this declaration. I need to go to my memory and allocate an integer storage area. And what? Int is how many bytes? 4 bytes. So I need 4 bytes of memory space, contiguous memory space, and I'm gonna call that address space X, all right, which is gonna have a starting memory location, and then I'm gonna store the value 25 in it. So that's what happens when you do int x equal 25. Now, so now you got int and a pointer variable PTR. This says, okay, now I have a variable called PTR. What's the data type? Int. But what is this PTR? Oh, it's a pointer. Now, that pointer can only hold what? An integer address. Okay? An integer's address. The address of an integer variable. Okay? So now I have a PTR pointer address. So now, what happened in here, it says PTR equals ampersand X. I cannot say PTR is equal to X because what? I'm trying to store 25 into PTR. If I do PTR, which is a memory location, is equal to ampersand PTR, ampersand X, Now I'm saying the address, the integer, which is X, the integer address, which is X, is equal to the integer address of PTR. Okay, so now I'm storing the integer address into an integer pointer. Everybody understand that? But then when you go down here, see out the value of X. If we want to just write the value, we just write out what? X. If we want to write that memory location, we could write out PTR, or we could write out ampersand X. Everybody understand that? PTR, the value of PTR and the value of ampersand X is the same. Everybody understand that? All right. He said, okay, well, Mr. Buster, why would you say that? Okay. So if I say int, and I'll do ampersand, I'll just keep it PTR. All right. So I got a pointer variable. So now, before I output, oh no, I'll do it before. I'll do it up here. All right, so I'll say int PTR. So now I have a pointer address of integer data type where I can store any integer value into this pointer. So now, before I do my couts, I'm gonna say PTR is equal to ampersand, remember, X. All right, so now I could see out age, but I could also see out, I'll just do something like this. All right, I'll do X is equal to age, but do I have X up here? No, I'll do, I'm messing up. We're doing age. I don't need to introduce no new variable. All right, so I'll do that because I don't want to introduce a new value. So age is integer. Age going to be stored in age address is going to be stored into this pointer address. I'm gonna output age, but then now I'm gonna output the address of age, if I can get my fingers right. Okay. All right. And PTR. All right. So now, when we run it this time, all right, and see we have our address, right? But I can also do what? The same thing, see out. Oh, let me copy this. I'll take this out. I'll copy this. I'll paste this down here. And then I'll change this to ampersand X. So what? This statement and this statement, not X, age, my fault. My X is in my head. All right, age. So this value and this value should be what? The same. Okay, and don't matter what number. So you see what I'm saying? PTR and ampersand age, which is the address, is identical, is the same. All right, so that's our pointers, and that's how you can print out that address using the PTR. But what? That memory address was stored in the PTR. Now, so all it's saying is, just like when we did jelly donut, all right, when we do the ampersand X, all right, is equal to PTR, it took the address of X and stored into PTR, all right, and it allows us to access that memory location. So X, which is located at that memory address contains the value 25, all right, which we saw in our program. One real benefit of pointers is that they allow you to indirectly access and modify. Now, we're going to see why we can actually modify the value at that pointer address, all right, it's pointing to. PTR could be used to change the content of variable X using the indirect operator, which is the asterisk, all right? So look what happens here. Look at this small program here. We have an int variable here, okay, which is X. Now, note, just keep and kind of follow me along. Let me see if I can make it a little larger way you can see it. Okay. All right. So if we look at this, int X equal 25. This is just a comment. All right. Int pointer PTR. So now you got a integer pointer. Now it says ampersand X is equal to PTR. Okay. I output X and I output asterisk PTR. Now, asterisk PTR gonna output what, class? The actual value. So now what? I don't have to reference X. I could just, to say C out X, I could just say C out asterisk PTR. Okay, so I could go back here and watch this. If well, that's the address. If I do asterisk PTR, right now, before I was printing out the what? The actual address. This gonna allow me to print out whatever value that I have at that memory address. So now when I run it, I should get 25 then the address. Well, 25, 25 then the address. See, 25 was the age. 25 is this part here. See this one, address of age. I just didn't change it. Address of age, that's this, asterisk PTR, 25. And then the address of age, which is the ampersand, that's this one. It's just that I didn't change this. I was just gonna say value. I'll change that to value. All right, and then I'll run it again because it's kind of deceiving. All right. It's right here. So, okay, in the age, I'll put 25. And see, look, age, value of age, 25, and the address. So you see, you can actually print the contents of that pointer or at that pointer address, all right? And it knows that what? If it's int, I gotta grab these 4 bytes. If it's double, I gotta grab these 8 bytes. If it's char, I just grab that 1 byte. So that's why it's important, and it tells you can only store like data types into that pointer, that declared pointer. If I declare it to be char, I can store a char address, a pointer. If I declare it double, I can store a pointer, a double. I can store a double address into that pointer. All right. So you gotta make sure you keep that in mind. So, but now, look what happened. It said what? I outputted X. I outputted the actual content at that pointer variable or that address, and it printed out what? The value, which was 25. But look here. Now I'm saying what? Asterisk PTR, right? So the value or the content at PTR now equals 100. So I've just done what, class? Anybody? What this statement just did what?
That's the address location of PTR to 100.
The first part is wrong. It changed the what? Not the address, but the what? That asterisk tell you to reference the what? Remember up here? When we talked about it here, I think it was here. The address allows you the actual value, right? It actually allows you to get to the content. So what happens is X was 25, right? We declared it to be 25. we outputted the contents when we did asterisk PTR. But then we went down here and say asterisk PTR, which the contents is equal to 100. So we have just overwritten 25 with what? 100. Because we working with that the value. When we do the asterisk in front, we working with the value, right? So let's look at the program. So in here, I could do this, all right? I'll just do it down here. And so we got our address, we got our whatever, and then I could say asterisk PTR is equal to and I'll just put the 100 like they doing it. But we really know that when we input the age, it's going to equal to whatever we put in. But then this going to change it, and then now I can come here and I can output, because being that I'm still pointing. Well, I want to print the value of age. I want this one. So cut this, copy this, and print this here. So what this will do, whatever, I'm gonna put in 25. So when I go here to here and input 25, it's gonna output 25. It's gonna output 25 again. Then it's gonna output the address. Then it's gonna say, hey, at that memory location, but now don't deal with the address, deal with the actual content. Change whatever's there to 100. And now when I output, it should output what? A 100. So let's run it. Down here. So if I put in 25, all right, hit enter, look. And that's without me ever having to do what? Mention or reference what? Age. Everybody understand that? I didn't even reference age to do anything to change it. I did something at the what? Pointer level, right? Everybody see that? And I can add an expression, 100 plus whatever, or say 100 times divided by whatever it is, it'll be stored into that pointer, all right? So, now run it again. And if I put 25 here, all right, but the other thing, 100 divided by 2 is 50. So see, it still calculated this and stored in the, change the content because I'm dealing with asterisk. Now, if I take this asterisk off, this has to be an address. Everybody understand that? This would have to be an address if I take this asterisk off here. Like here, when this is just PTR by itself, I have to make it equal to some address, all right? Now, partners get a little, now I wouldn't say confusing, but it get more in depth, all right? Because look what happened here. Well, they printed them out. They printed out X and Y again. So they just showed you how they printed the value one time and printed it again. Now, this just goes in and if I could get this thing right. Give you explanations as to what happened, and which we saw what happened. So if we look at this, all right? Right. All right. So if we look at this, you know, we have C out, and what we outputting here, the actual what? Value or contents at that what? Memory location. Because of the what? PTR. Right here, we outputting the what? The address, right? Because it's just PTR. Remember, PTR by itself, if it's a pointer, is equal to ampersand, whatever variable. So right here, we're just printing out the what? Memory location. But then this statement here, what are we doing? We are actually overriding the content that is currently there with what? The value 100, because of this what? Asterisk. Everybody understand that? So you got these three statements, right? All right. All right. So now, this is a program. Let me see if I do it this way. All right. So this is a program, all right? referring pointer referencing different variables. Now, see, this way it can be tricky. All right, and I'm gonna point out some spots in it in the program that I want you to see. All right, here we have int x, y, and z. X is 25, y is 50, z is 75. At this point, we said what? Then we have a pointer variable, right? An integer pointer variable called PTR. So
Jake's not feeling well today, so he's not here.
Who that? Oh, you tell me. All right. So if we look at this variable, look at this statement. We setting what? The address of X to equal to what? I mean, PTR to equal to the address of X. Everybody got that, right? Everybody understand that? Then, what are we doing here? We're saying whatever is at that address, because we got asterisks, so the content of PTR, we're going to add it to 100. That's the plus equal. That's like saying whatever's in here, which is what? 25. 25 is equal to 25 plus 100. So really, I'm changing the content of X to 125. You got what I'm saying? Without even dealing with X. But look at what happens. At this point, I didn't create a new pointer variable. I said what? Ampersand y is equal to PTR. So all of a sudden, I've changed the what? I've changed the
value of y.
No, I've changed the address of PTR to equal to y address. Right. You understand what I'm saying? So now rather than me dealing with X or referencing X, the contents or the address of X, now I'm able to access the contents of what?
Y.
Of Y by using the very same what? Very same pointer reference. Everybody understand that?
Yes, sir.
You see what I'm saying? So that's how I can get more in depth. You know, you don't have to create, if you got 15 different int variables, you don't have to have 15 different pointer variables. You understand? Depending on what you're doing, you can have just one and just use that pointer variable to reference the address and do what you need to do. So in this program, we had 3 int variables, but in 1 pointer variable, and depending on the given time, at this point, we're moving the X address into that pointer and manipulating the content. Then we move Y address into that pointer, and then we manipulating the content at what? At Y. So look at this. This is the same statement as this one. Your asterisk PTR is equal plus equal 100. This one, asterisk PTR plus equal 100. But the difference is this is referencing X, where X is 25, and this one is referencing 50, you know, Y, where Y is 50. So 25 plus 100 is 125, but 50 plus 100 is 150. So you see what's happening here? And then it says ampersand Z is equal to PTR. So now it's taking the address of Z and putting it into PTR. So now I'm referencing a different look. My pointer is at a different reference point, and now it's saying what? Whatever is at Z, add 100 to it. So what? 75 plus 100 is 175. So everybody understand what happened here. The value of X, Y, and Z was incremented or changed not by using the actual variable, but referencing the address and then using the pointer to actually referencing the value at that pointer to change the value. Everybody understand that? So see how pointers can work with programming, and pointers, as I say, you're working at a low level and it runs faster than you declaring variables, X equal whatever, doing whatever. pointer variables work, allow your program to run faster. So looking at this, PTR equal ampersand X. This is valid. This, what it does though, it takes the address of X and put in PTR. This take the address of Y, put in PTR. And this take the address of Z and put in PTR. Now, depending on which address is in PTR, going to determine what your results will be. Right, class? So if I'm at if I did ampersand X, if I stored the address of X to PTR and I executed this statement, I would get 125, where X was 25, Y was 50, and Z was 75. If I'm pointing to the Y address and I execute this statement, I'm gonna get 150. If I point to the Z address and then execute this statement, then my results will be 175. But you got to remember, ampersand Z, PTR equal ampersand Z is not changing anything in X and is not changing Y. It's working with what? PTR now works with what? Z. Anybody understand that? So I changed that address to the Z, to the variable of Z. I'm only working with the Z, not X or Y or any other variable. All right? So you notice that these statements are indirection that in these statements, the indirection operator, which is the asterisk, is used. This means that you're working with PTR, but not working with PTR, but rather the actual item or content that is that PTR points to. All right. So if I do cout PTR, I'm outputting the address. If I output asterisk PTR, I'm outputting the content at that memory address, which would be the values that's stored there. Okay. So 3 different uses of the asterisk that we know so far. Looking at this one, you multiplying speed time time. So you're using it in an algebraic expression. This one, you declaring a pointer, all right? You declaring that PTR would be a pointer variable. And in this one, you're saying, okay, reference that content at PTR, whatever address I'm at, take the content and override it with 100. Okay, so indirection operator. So you got 3 different ways that we should know of how we use that asterisk. All right. All right. Arrays and pointers. What are their relationship? Okay. As we've learned in chapter 7, an array name without brackets, all right, and a subscript actually represents the starting address of an array. Okay. Now, therefore, an array name is actually a pointer. Okay. This is done by using the array name preceded by an indirect operator. So look what happens. When I cout this, I'm gonna be outputting the actual address of that array, just like the pointer. It's the pointer. Now, well, no, this will print out the value. Okay, the value. Now, because numbers in the above code works like pointers, all right, to starting addresses of the array, the first element is retrieved, all right, when numbers is dereferenced, all right? Remember, array elements are stored together in memory. And just the name by itself would give you the starting point, okay, of the array. All right. All right. So now let's do this right quick. We go here to show you. Let's I could leave it in. Let's take it out. Let's do an array. All right. I'll take this out. I'll do int num equal. I'll say 10, 20. Don't matter. my now, I can implicitly declare this, but it don't matter. I'll just put the 10. Why is this giving me this here 20? Oh, semicolon. Okay. And then I'll do, all right. So now, so I have this. And remember it had what? Yeah, I do C out, if I could type. All right. But I'm gonna output ampersand. All right. So now.
Still need the.
Oh, my directive, yeah. All right. So now, this should output what? 10, because it's the beginning. So when I do debug and I run it, it should give me the first. Uh-oh, I got an error. Let's see. No, what's the
We
error?
still have get age in there, which I think is causing an error.
The who?
The get age function.
Oh,
I don't think
yeah. Oh, at the top. Well, is it? Yeah. You're right. But it should. I'll just take it out though. And whatever. Comment this. I'll take that out. Right. Okay. I think that's it. All right. Yeah, I forgot that function. All right. So let's run it. Okay. So see what happened? Now, you got to understand what's happening here. Num is what? The actual array, right?
Right.
An array is a pointer, right?
Right.
So the name of the array represents the starting point of that of the address, right?
Yes.
So now when I say asterisk num, it's saying, okay, give me the address, because you're always going to get the beginning address, not all of the other addresses, right?
Right.
So when I do asterisk num, it says, okay, it's an array, it's a pointer. Okay, I want the address of the beginning address of num. And this, well, no, not the address. I did the asterisk. So the asterisk says the content of the first one. And num, what, 4 bytes? So it grabbed that and it gave me that output. Okay? So everybody see what happened here. That's an array. And this says, now give me at the first position, give me the content. All right? Because the name of the array is the first address position. All right. So that's what the notes was trying to depict at this point, telling you why the name of the array, and this would actually give you the value of the first element. All right. Now, it says it's important to know that pointers do not work like regular variables, okay, when used in mathematical statements. And what they mean is, if I multiply an array of the contents of an array, I'm actually jumping X number of bytes, depending on the data type, to move to the different memory locations. All right. So it says in C++, when you add a value to a pointer, all right, you are actually adding that value times, all right, the size of the data type being referenced by the pointer. And like I say, that has to be true, because in order for you to grab the data in each one of the elements, it has to move what? By the byte size. Otherwise, your data wouldn't actually work. Your data you wouldn't be able to grab the data. So what it's saying is the first position, if it's an int, you got from that starting point 4 bytes. The next position, from the end of that other one, which is the starting point, 4 more bytes. Move on, 4 more bytes, and on and on and on. So it tells us, therefore, if you add 1 all right, to numbers, and it's talking about numbers, which was the array, right? You actually adding 1 plus the size of, all right? You adding 1 plus the size of. So of the number. When in ours was int, so you're really adding the size of int is 4. So it's 1 times 4 is moving over and move, and if it's 2, you're moving over and on and on and on. So if you add two numbers, all right, well, if you add 2 to numbers, the result is numbers plus 2, all right, times size of, all right? But this is what you see, or this is what you would do, but no, this is what it actually is doing, okay? Numbers plus 1, all right? Then it's time the number of the byte sizes, all right? So let's go back to, well, let's look at it. This automatic conversion means that an element in an array can be retrieved by using a subscript or by adding its subscript to a pointer, to an array. If the expression ampersand number, asterisk numbers, which means numbers, asterisk numbers plus 0, that'll retrieve the first element, then what? This one, asterisk numbers plus 1, will retrieve the second. So let's look at this. All right, let me close this up. So click here. So now, if I do this, but now remember in math, right? You got to make sure your grouping is right, correct? So I cannot just say num plus I'll say 4. I cannot just, that's equal.
Was it the preheat lines? Was it the preheat where y'all had the issue last time? When I talked to Jake about it, it sounded like you had the vaporization at the point where the HAFO was injected.
Oh, that's not class, huh? Oh, I'm thinking.
Oh, that's where you had the kickback.
So, man, you're kind of not muted right now, bud.
Okay.
Yeah, it was. Yeah, tell him. Yeah,
Okay.
go ahead. All right. So, what happens is I have to group this. All right. If I don't group this, it's gonna take what 10 and add 4 to it. Correct.
Okay.
Right.
Everybody else because of precedence. All right. So you got to be aware. So when I do this, so now what? That's the what element going to be printed? It's going the first one was 0
for fifth element.
Right. So the fifth element is going to be printed. You got what I'm saying? So if I run this, let's see what. Okay, debug. Yeah. You see what I'm saying? 1, 2, 3, 4, 5. So the fifth element, right? So now the thing is this, all right? And we deal with arrays all the time. What I can do, I could do something like this, right? For int x equals 0, right? X less than 10, x plus plus. But watch what I do here. Okay. Close this, but watch what I do.
Put down to +1 at that point.
Huh? Do what?
No, never mind. I was my mistake. Right.
Right. So you see what's happening? When it's 0, it's gonna be what?
10.
All right. So what happening? I'm manipulating my array by by doing it this way. So watch. When I run it, oh yeah, I got it in line. See what happens? I got so many spaces in between. So I've just printed out each one of my elements in my array by using this asterisk, right? And then actually adding 1 each time to my array. So I'm at the 0 position, which is the asterisk num, but then I'm adding 1. Well, first time is 0, so I'm still at the beginning point. I add 1, it jumped 4 bytes. I add 2, I move another 2 bytes. So you see what happened? you can manipulate your arrays in this fashion. And what? You don't even see a subscript in here, right?
Right.
Okay. So and like I said, a lot of times, a lot of that programming style, like I said, if you choose to do stuff this way or whatever, but normally the normal way you use your subscript and you move on. All right. So now, so here, and it shows us where we have an array called numbers, but this one is with a shorts. And we know shorts is what? 2 bytes. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. So what? Numbers, asterisk numbers is the starting address as the first position. All right, so that's num sub 0. So even if I add plus 0, I'm still at what? The 0 position. Plus 1 will move me to the what? That next element. Then plus 2 add 2 more bytes and put me at this location. Plus 3 put me at this location. Plus 4 put me at this location. And it's always the starting address, and then it takes up on the rest. All right? So the parentheses, like we said earlier, are critical when adding values to pointers, okay? The asterisk operator is preceded or has precedence, all right, over addition, subtraction, division, whatever, right? It has precedence. So if you would not put this, all we would do it would be add one to the first one, 2 to the second, and I'll show you in a little while, 3 to the next, all the way till we get to the end of our array. So like say here, if I would take this off of here, so all it would be doing, and I'm gonna take this up. All it was doing is saying the first time is 10, the second time is 10 plus 1, which is 11. Next time 10 plus 2, which is 12. So that's all you would be doing, all right? Because you're referencing the first one all the time. You understand what I'm saying? Everybody see this. And it's important to understand this, class. So the first time through is asterisk num plus 0. And that puts me still at the first position and 0 to 10, okay? Going through the next time, x is 1, so asterisk num is the first position, which is 10. Add 1 to it, makes it 11. Next time through, x is 2, asterisk num, it's just 10, plus 2, it gives you 12, and on and on and on and on. So you see how those parentheses, the parentheses matter. They make a big, big, big difference. And now if I do it this way, now it's going to take, each time it's going to take num plus 1 plus 0 would be the first address. Num plus 1, it jumps 4 bytes. Num plus 2 jump to the next 4 bytes. All right? So it makes a big difference. All right? And if you notice here, it's down here. So here, this is the content, 10, 20, 30. So it's moving what? To every beginning address, all right? Okay, any questions about that? Any questions? What time class end? Because see, man, I'm going on.
11:15 is when it's supposed to be over, but it's
all
coming.
right. So let me, well, I'm gonna go with this one. I tell you what, I'll stop because there's another way you can do it also, but we'll look at it. We'll look at it on next class period. All right. So, and this is on this page. It's just telling us this asterisk array plus index, which index would be a subscript, is equivalent to array subindex. Same difference, right? Same exact difference. And in your program, I think I have you taken your program for this assignment, and we never went over it yet, but I could post it for you to look at. I think it's this one. All I'm doing is telling you to go to the functions where you're manipulating your arrays, and rather than manipulate your arrays using an index, manipulate your arrays using the asterisks. So like where you looping and you outputting your name, year, and whatever, Rather than use subscript, do it this way. And like I said, it's just an easy little fix. But I want you to be able to go in and do it. Because it might look funny or whatever, but this is equivalent. This is equivalent to this. All right. So we'll pick up on this on next class period. Won't sign no programs. I'll just open those two up. I won't sign them. You can read through them, the pointer programs, but I'll assign them once we complete, go through all of this and where you can understand a little bit more. It talks about where you can compare the different array positions or whatever. So we'll and then passing the arguments. So don't worry about the assignment. I'll post them, but I won't give you a due date on them. I'll assign them next week. All right, and then I'll also assign the test. But you can get started on them. See, that's the thing. Even though I put it out there, you might say, "Oh, well, I'm gonna wait till he assign it." But you're gonna have the time to do it. Start on it. Look at the notes. Ask questions in class. And you'll be more prepared. All right. So everybody, just read over the notes, study the notes. Like I say, it could be a little confusing. And like I say, on next class period, we'll complete the chapter, and I'll actually give you a deadline for the assignment. All right.
Yes, sir.
All right. So have a good day.
You too, sir.
All right. Okay. Anybody with questions? All right. So I'm gonna end it.